many interesting things. So we had a lot of interesting subjects of theory covered here. Kind of a big catalog of phenomena. I mean, these were things that seemed like highlights to me. A lot of great, interesting ideas about kind of generalizations of topological insulators, especially biofermions, Majoranas. Several talks talking about, including by Guignat and Nandini, about competition between spin-orbit coupling and exchange and how that might lead to interesting phase transition. We had a nice full orgy of Kitaev talks and posters. Of course, the dates have been present everywhere, and this morning we did some conference tonight, and so this is all great. Great. So it's all great stuff. I could go in and review, as I did very conscientiously and review everything that was talked about in theory, but maybe I won't. Make a few comments. This is the end of the conference, so we're all probably feeling good about that, but many of us who are staying here will know that this is almost just the beginning of the program. So we have a lot of time to really achieve things. And I'd like to point out that we've already achieved one thing, which is so far unparalleled, which is we brought the great Guignat to America. I had some fun with Photoshop. But maybe we accomplish some other things, I hope, over the course of this program. I guess I can't resist just mentioning a couple of things that occurred to me as we went along, so that we have something to talk about if we actually have a discussion. Or not, we can quit. So we had a lot of nice talks about biofermions, which is beautiful. I'm just amazed at the progress over the past year or two. Once again, so from the theoretical point of view, it proves to me that we are really, really good at solving problems of non-interacting electrons. And there's still a lot of things to do there. I didn't come into it thinking I would like it, but I really like. I don't know if Drew is still here, but I really like this talk on quantum oscillations. Anton would not forgive me if I didn't tell you all that you would cite him. Not getting cited sufficiently in this program. So, fix your act up. As Sakage-sensei pointed out in the last talk, we don't do nearly as well in this intermediate range of interactions, and I think if there's one message I want to get across in this talk is that we theorists need to do better to do something beyond weak interactions. A few of us have made kind of crazy proposals. You can judge for yourself how crazy each one is. This is the one I was guilty of a few years ago. And today would like me to explain, but I'm sorry I'm not going to. And we heard this one at the beginning of this conference. I think it's okay to have crazy ideas in this field, but we should try to do a little bit better at trying to figure out how to make them less crazy. And can we do better without throwing the baby out with the bathwater, just going back to free electrons in one way or another? Kitaev stuff. Where was a great set of Kitaev talks. You saw these beautiful pictures from Maria Hermann's posters of all these little models and phase diagrams galore. So complicated, the kind of collecting. So I kind of wonder, besides making these very fancy phase diagrams, are there some non-zoological questions we might address? To me, it's obvious what the biggest question is for theorists in this Kitaev subject, which is why did Kitaev leave the KITP? This is a very difficult theoretical problem. maybe there's some more questions we might have for Alexei if we can ever get him back. We've seen a whole bunch of great candidate Kitaev-like systems, and maybe we might even be convinced that many of them have very strong Kitaev interactions, but can we actually get one of these systems into the spin-liquid phase? And actually, Hide showed us some interesting experiments under pressure, hydrogen. Maybe he's doing that. It's not all that explored yet. The materials we mostly heard about during the program we're all actually ordering. Can we do some theory that's a little better than just these semi-classical calculations, or kind of working out the details of Kitaev's exact solution, which he taught us about? Actually, first learned about Kitaev's solution in this room. This room? Founder's room? Okay. Yeah, I'm not sure it's the same time. I might have learned before. That's it. During the exotic? Yeah. Might have been before. Pretty sure I learned in this room. But, I think we should try to do better. The one question I just will say, a little bit of science about is, what does it mean to be close to the Kitaev quantum spin liquid? So, we've seen experimentalists work really hard to make this beautiful material, try to grow perfect crystals, do super hard experiments, put under pressure, stuff hydrogen in, incredibly difficult things, and then the thing orders. And they work really hard to figure out this order. But they really wanted a spin liquid, so of course they're desperate to say, can I find some remnant of this spin liquid in there? They'd like to say we're close. We look for something, some blob, some plot. That's close. I think that it falls to us theorists to at least tell them, what does it mean to be close to the Kitaev spin liquid? How could you actually tell? This seems, I don't think people have thought carefully enough, right? Just to give an idea of some of the difficulties of it, when I think about something being close to the Kitaev spin liquid, I imagine there's some Hamiltonian, which has, maybe if we actually were to write it out and we knew what it was, would be close to the Kitaev model, but there's some other interaction that I call G, and it's different from that in the Kitaev model. It's pushed it a little bit away, so the actual ground state is not, even in the spin-liquid phase, it's ordered. So that means there's a phase transition between, and the natural guess is there's a quantum critical point there. People actually studied this numerically in Kitaev-Heisenberg model, for example. Incidentally, nobody understands this quantum critical point, as far as I know. I asked Chenka if he understands it this morning. He said he doesn't, so therefore nobody does. I think that's a safe bet. But anyway, there's some quantum critical point there. And what do we actually know? Well, we know that in the ordered phase there should be some spin waves at low enough energy. In Kitaev spin liquid phase, there are all kinds of fancy anyons that are doing interesting things. But what general theory tells us, when you have a quantum critical point, in between there's some more complicated excitations which are different from those both of the spin liquid and the ordered phase that are some quantum critical excitations, and they sit in this famous fan. So if we imagine we're on the ordered side but close to this Kitaev spin liquid phase, if we go up in energy, we don't see the excitations of the spin liquid, we see the excitations of the quantum critical point. Is there any reason to believe at all that we would be able to see remnants of the spin liquid if we're close in this sense? Maybe you're lucky there's some high energy excitation that's so high it's already kind of at the top of the span and it continues across, but there's no obvious reason why that would be true. I could come up with a slightly different situation. So here's the usual thing we do as theorists. We mix up every possible energy scale. We write energy, which might be a neutron energy. We write temperature. We put them all on the same axis. Maybe it's not the same. This could be a first-order transition, although I don't think it